times e to the power of minus e minus tau over k in the tau plus q0 e to the power of minus t over k. Okay. Just note that I changed the sign here because, for formalism, I wanted to get t minus tau instead of tau minus t. And if you look here, t minus tau, I want to get an expression that is similar to this one. So I changed the sign, basically. Okay, this is my model. Basically, we now have an explicit relationship for Q, and we have on the right-hand side forming Q two terms. One term is independent of rainfall, it's the second one, and we can call it a depletion term. And in Italian, depletion is esoteric. I'm not sure depletion is the correct word in English, I hope you understand. It means it's a term that takes into account that the river flow at time zero is slowly decreasing to zero, tending to zero. Because if you see, for increasing time, this term, which represents the propagation of the initial conditions, tends to zero. It's the flow of time zero, the river flow at time zero, that is slowly decreasing to zero. So this is the first contribution. It's independent of rainfall. The second contribution is given by rainfall, that is multiplied in a summation by coefficients given by 1 over k times e to the power of minus e minus tau over k. Okay. Now, what happens? Let's ignore, from now on, let's ignore this recessing term or deflation term, as I called it. Let's ignore it. Now, there is a question to analyze, to better understand what is the behavior of the river flow simulated by this model. There is a question that we may ask ourselves. What happens with constant rainfall? So what happens if it starts raining with a constant rainfall in time? In this case, this is a useful case to analyze because we can easily compute the integral. And we can then derive a graphical representation for the hydrograph. Okay, let's see then what happens with constant rainfall. So with constant rainfall, we can write that Qt is given by the integral between 0 and t of, first of all, let me bring rainfall outside the integral because it's constant. So I can, for simplicity. And then we get 1 over k times e to the power of minus e minus tau over k, the tau. Okay, so we can write Qt is equal to t now we have to compute the integral of 1 over k e to the power of minus t minus tau over k in the tau. And I would say that this is equal to e to the power of minus t minus tau over k. And that's it. Because if you compute the derivative of this term, it's given by the term itself, which you can find here, and times 1 over k, which you can find here, but there is a minus. So if there is a minus, probably I should put a minus here. Yes, I think so. We will realize if it is true. Okay, so let's compute it at the extremes 0 and t. And basically this becomes qt is equal to e that multiplies. Okay, first term is if we substitute tau with t, we obtain e to the power of 0, which is 1, so it should be minus 1 sorry?
Why the term 1 over k is disappeared?
Yeah, because basically it disappears because if you compute the derivative of this term, you basically get the same term, e to the power of minus t minus tau over k with the negative sign, which is here. But then you have to multiply it by the derivative of the exponent, which is minus 1 over k. And so you get already 1 over k here, and the minus changes the sign. It should be correct. I'm not sure of the sign, but we will realize now if the sign is correct. It seems to me that it's correct, but by developing the next steps, we will see if it is correct. And if you compute this term for tau equal to t, you obtain e to the power of minus t, which is 0. So it becomes e to the power of 0, which is 1, and therefore minus 1. Should be correct. And then we have a minus because I am computing in 0, so we have to subtract it. And then I have here minus e to the power of minus e over k. One second that I check is minus. Okay, this is fine. This is 0. It should be correct. And therefore it's clear that then this minus become plus. Okay. Therefore, it becomes qt is equal to p, which multiplies everything is fine here, but we should the sign is not correct. So basically, if the sign is not correct, it means that this should be like this. So 1 should be like this, and therefore the sign was not correct here. And so we should get here 1 minus e to the power of minus e over k. Okay, this is the correct representation. Now, let me think just 1 minute more on the sign here, because I want to understand why it was not correct. So, this is the yes, because it's the derivative of the exponent, it's 1 over k indeed. It's 1 over k. Yes, I shouldn't have changed the sign here. Okay, so this is the correct representation. Okay, now, what is the shape of this hydrograph? Qt against time. First of all, we neglected the term Q0, so the hydrograph starts from the origin. Q0 equal to 0. Neglecting Q0 means that Q0 is equal to 0. So the hydrograph starts from the origin. And let me put in evidence here on the y-axis the constant B, which is a volume of rainfall per unit time. So it's basically, I can represent it on the same axis as the river flow. And let me, given that it's constant, let me represent it in this way. And therefore this relationship tells you that for increasing time, the storm here, which is negative, vanishes, and Q tends to B. So basically you get an hydrograph that is done in this way. Which is fine. Which is fine, meaning that if you have constant rainfall and this rainfall is continuing indefinitely in time, you have an hydrograph that starts from 0, and then your tank starts collecting water. And therefore WT increases. And increasing WT brings also QT to increase according to an asymptotical relationship. And after a while, you get in a situation where QT is basically constant or very slowly increasing and equal to the volume of rainfall per unit time. So you get to a situation where the catchment gives back instantaneously all the rainfall that it receives. And of course you get to a stable value of WT as well, because WT is just obtained by multiplying QT times K, and therefore if K tends to P, then you have WT tending to P times K. So you tend to a stable situation where the storage of the catchment is unchanged in time and the river flow is unchanged as well. Good. Now let me now copy the relationship, the integral relationship here. I just copied this one by neglecting Q0. So it's Qt is equal to the integral between 0 and t of E tau 1 over k e to the power minus t minus tau over k in the tau. Okay, I just changed the order of 1 over k and p tau. Just change it. And now let me write back here the relationship of the time-area method. There is a change of variable that we have to make if we want to compare the two relationships, because here I'm using I, instead there I'm using p. So basically let me just take a change of variable by dividing 1 over a, by dividing the integral by 1 over a, and then I can write the integral between 0 and t of the, let me put the rainfall first, the t minus tau tau and the t and the tau. Okay, these are the two. This is linear reservoir and this is time area. Okay, notice that these relationships are very similar. And if you consider that the integral is like a summation, you see, first of all, one difference. If you look at this, at these two relationships, you may say, look, there is a big difference. P refers to the index tau, and in this case, it refers to the index t minus tau. But it doesn't change anything, because basically, remember that t is varying, tau is varying from 0 to t. So here, if you, in the summation that you obtain, if you express the integral in a finite form, here you have rainfall that is starting from time 0 and then reaches time t. Here you have rainfall that starts from time t and then goes back to time 0. So it's just the order of the elements that you sum that is changed. But basically, it doesn't change anything from the physical point of view. You have rainfall from time 0 to time t that is multiplied in a summation or in an integral for some coefficients. Okay, basically you have rainfall that is multiplied by some coefficients. And it doesn't matter if you start from t and go back to 0 to make this multiplication, or if you start from 0 and go to t. So this is not really a difference, it's just a difference in the order in which you compute this integration, but it doesn't make any difference from a physical point of view. The difference is in the coefficients, because in one case you have the coefficients that are given by the derivative of the time area curve with respect to time. And in the second case, the coefficients are given by 1 over k e to the power of t over k. T minus tau, but it doesn't make any difference because tau is varying, so it's an increasing time over k. So basically the two models are two linear models, because you see that the structure is linear. So they express river flow as a linear combination of rainfall. The difference difference is just in the coefficients of the linear combination. That's it. Okay, so you may have an idea. And the idea is to write a general form for the linear models, which includes both of them. And the general form of the model can be written in this way: Qt is equal to the integral between 0 and t of p minus tau h tau in the tau. You could write it in this way, or to make it even simpler, you could also write p tau, just p tau, because with a change of variable you can also write it in this way: p tau, h tau, to the tau. It depends on how you define this h tau, and that's it. Okay, and of course, as I said, this one is very general, and basically it could also include other formulations. You could write h tau in an empirical form by using an empirical representation, not necessarily a representation given by the time area model or a representation given by the linear reservoir. You could establish a series of coefficients for this linear representation, and in fact the literature proposes a lot of linear models that are based on different formulations for h tau. H tau is called is identified with the acronym IUH, which stands for instantaneous unit hydrograph. Why it is called the instantaneous unit hydrograph? Because it can be proved that the IUH is the response of the basin, the catchment, to an impulse of rainfall of unit volume. So basically, if you have a yetograph, IT, which lasts for an infinitesimal time at 0, So the duration of the hydrograph is tending to 0, but the volume of rainfall is a unit volume, and therefore if you want to represent this hydrograph is a Dirac delta function. So it's infinite rainfall, but if you integrate this rainfall over time, then you get a unit volume of water, and therefore you may represent it with the classical representation of the Dirac function. Then you get a response from the catchment. So in this case, unit volume means, for instance, 1 cubic meter of rainfall. And then, if this rainfall lasts for a time that is tending to 0, then you get a response from the catchment. And it can be proved by simply looking at this relationship, this integral relationship, where you have just one infinitesimal rainfall which is different from 0. By looking at this integral relationship, you see that h tau is the response of the catchment to this impulse of rainfall. And in the case, for instance, of the linear reservoir, you can draw this response. If you put here h t over time, you start from 1 over k, and then the IUH tends to 0, you see here. And if you start from time 0, then you get 1 over k as starting point, and then if you increase time, you go to 0 because this term is an exponentially decreasing term. Okay. That's it for what concerns linear models. And given that this is basically one first conclusion of this subject, so one of the topics of this subject was linear models, I just would like to make a check with you if, because you know, some years I got the comment from the students that the course was too trivial. Some other years I got the comment that it was too complicated. So, and this is because, you know, in your master degree program, the situation is atypical because depending on the students that you have in the room every year, you have very different backgrounds, as I already mentioned to you. This is a problem that, not a problem, it's a feature that we are experiencing also in the other master degree programs, because until 10 years ago, let's say, up to 10 years ago, the situation was much more standard. We had students from the region, basically, from this region, Emilia-Romagna, and a few students from other universities, and let's say that 90% of the students took all of their studies in Bologna. Now, even in the courses in degree programs that are taught in Italian, we have two different, we have the bachelor and the master, while up to 10 years ago we had only one course that was 5 years long. So even in the courses that are taught in Italian, now we are experiencing in the master programs this difference in backgrounds, which on one hand is a great advantage because it allows you also to compare different experiences. On the other hand, for teaching, of course, it makes the situation a bit variable, a bit variable. So sometimes when I started teaching this course, it was 4 years ago, and I think this is the 4th year, yes. So as I told you, sometimes I got the comment at the end of the course that it was too complicated, and other times that it was too trivial. So I would like to get your opinion, and maybe that you are too shy now to speak, but do you think it's too trivial or it's fine? It's fine? Yeah, of course, it's difficult that you say. But if you have any comment on that, also on the English, just, okay. let me know. Basically, my target is to make things very clear, but not completely, because you know, otherwise it takes too much time for me to explain in detail. For instance, like here, the instantaneous unit hydrograph, I just said it's an impulse response, and I didn't, it's the response of the catchment to an impulse of rain, but I didn't go into the details. So, because otherwise it takes half an hour to prove with analytical derivation that indeed it's a response to an instantaneous rainfall. So basically I wanted that 90% of the things that I say should be clear, and if something is not completely clear, it's fine. But if 50% is not clear, it's not fine, okay, basically. And when you see that some issues are not completely clear, please feel motivated to go in deep, in depth, because, you know, if you are a very good student and you find only a few things that are not clear, you should be motivated to understand also the things that are not clear, because this is your autonomous development of your background. So you can't expect from a master degree program that everything is clearly explained. There are some issues that need to be explored by you. Otherwise, you know, the program of the subject is too limited. So sometimes I make the decision to broaden, you know, the view, to broaden the number of topics that I'm dealing with, but of course this means that not all of them are explained in detail. Usually, I should have the perception of what I explained clearly and what is left to your initiative. And basically, when I ask questions to the exam, I know what was explained clearly, and I start with these questions. And then I leave more difficult questions to the end of the exam, only if the student is very good. So if I realize, I like also to have some questions that I didn't explain in detail, to be able to check if a student is very good, if he or she is extremely good, because the difference is the louder or not, basically. So I like also to have something that is not really explained in detail. So the meaning of this course that I just made is that, of course, you shouldn't be concerned again if something is not fully clear, but if you didn't understand anything or almost anything, then yes, please let me know, because it means that something is, needs to be tuned. Okay. Now, I would like now to relax a bit by dealing with an easier topic, because I'm not finished with the rainfall of models. I have another class of models that I want to introduce to you. But you know, this required quite heavy mathematical development, and the next one is as heavy as this one. So I really don't want to put in the same day too many difficult and mathematical things. So basically, I now would like to shift a bit on a topic that is related to rainfall of modeling, but I want to postpone the introduction of a new model. And let me explain better. I think that you clearly understood, also because I told you that we have parameters in our models. And not all the hydrological models have parameters, but most of them, the very great majority of them, they have parameters. And the presence of a parameter is clear if you look at the linear reservoir model, where you have K. It's clear that K is a parameter. If you look at the time area, it's less clear because you know, the parameter is given by the runoff coefficient, which, by the way, is also included here. So basically, I have an inner parameter in both these models, the runoff coefficient. And then I have an explicit parameter in the linear reservoir, which is K. So K is clearly visible. But don't forget that in the linear reservoir, you also have the runoff coefficient, or whatever other way for computing a net rainfall. Then you may ask me, but what is the counterpart of K in the time area method? Because you may say, you said that the two models are very similar, except for the shape of the instantaneous unit hydrograph. So you may say, what is the counterpart of K in the time area? And my reply is, look, the difference in these two models is the instantaneous unit hydrograph, which is a parametric one in the linear reservoir, and is instead given by a function which is not immediately parametric, namely the derivative of the time area curve over time in the time area method. So basically my reply would say, if you ask me what is the counterpart of K, I would say, how do you define this derivative of the time area curve? This is a function. So you may define it empirically through the isochronos, as I explained to you. So you may draw the isochron lines and define empirically this derivative. But then we already discussed the fact that you choose a velocity value in the catchment, which may vary depending on where you are in the catchment. It's not varying over time, but it may vary depending on if you are on the upper catchment or the lower catchment. So you have to define a velocity. So my reply will be, it's that velocity, the parameter. And if the velocity is varying in the catchment, it's actually given by more than one parameter. So basically the parameters for the time area method, besides the runoff coefficient, are in this description of this derivative of the time area curve.